Okay, so in the last video, we talked about the integral as a function. So given a function little f and a is fixed, you think of that as a constant, then I can define this function capital F, and the function is defined to be, for the input x, the output is this definite integral, the integral from a to x of f of t dt. And so what this function is measuring is, let's say this, if this is y is f of t, this axis is t, then, and this is a, then what this function measures is I go to x, I look at the interval from a to x, and the function, the output is this signed area under the curve. Okay, so if we have a function, we can ask calculus questions about this function, right? So we can ask, where is the function continuous? What are its limits? And the question that I want to ask in this video is, what is the derivative of this function? Okay, so I want to ask, what is the derivative of this function? And let's say we evaluate the derivative at c. So what is the derivative at c? Okay, so I want to ask, what is the derivative of this function? I'm just going to use the definition of the derivative, right? So let's write that down. It's the limit as h goes to 0 of f of c plus h minus f of c divided by h. Okay, just like any other function, I'm taking its derivative in exactly the same way. It's a function, so I can take its derivative. I use the definition of the derivative. Okay, so let's try to understand what this limit is. So in order to understand what this limit is, we have to understand what each of these terms represents, okay? So here, let's consider the first term here. So that's this f of c plus h. I have my function y is f of t. It looks something like this. Y is f of t. And f of c plus h, well, it's the integral from a to c plus h of f of t dt. So it's this signed area under the curve between a and c plus h. So it's the red shaded area here, right? The integral from a to c plus h of this function y equals f of t. So here, the curve is representing little f, okay? And then this capital F is the area, this area that's shaded in red here, right? So that's, okay, so that's the first term in this derivative. Now let's think about what is the second term in this derivative. So f of c, that's, by the definition of this function, f of c is the integral from a to c. And so this is c plus h. Let's say this is c. And so the integral from a to c of little f of t is this blue shaded area, right? And so what I'm doing in the numerator, f of c plus h minus f of c, is I'm taking the red shaded area, so f of c plus h, that's the red shaded area, and I'm subtracting off the blue shaded area, f of c, and so now what's left over is sort of this sliver of area. So this is going to be the area of this sliver from c to c plus h of f of t dt. So I'm taking the big red shaded area, I'm subtracting off the big blue shaded area, and this is just this area, right? And then I'm dividing by h, right? So what I'm doing is I'm taking the area of this thing, I'm dividing it by h, and that's my derivative, okay? So that's the derivative at c. So now I want to understand, what is this area between c and c plus h? So what is this area right here? This one, starting it. So you can think that if h is small, recall that I'm taking the limit as h goes to 0, right? So these 2 points are getting squeezed together, okay? So if h is small, you can sort of think that like f is not going to change very much. I'm assuming that f is a continuous function right now. So if h is going to 0, by what continuity means, the y values here are going to tend to a distinct limit. They're going to tend to this y value. They're not going to be very far apart from each other. So if h is small enough, these y values will be very close together. And so this shape is almost like a rectangle. So this is going to converge to a shape that looks like a rectangle. The base of this thing is h, right? It's going from c to c plus h. So the base of this rectangle is h. And now I can take any y value here to be the height. What I'm saying is if h is small enough, all these y values are very close together. So let's just take f of c to be the height. So this height will be f of c, this height right here. And so this limit as h goes to 0 is going to be the limit as h goes to 0 of this thing that's tending to the area of this, so that's approximately f of c times h, and then I'm dividing by h. And the h's cancel, and so this is going to become just f of c. So this function, which was defined to be the integral of little f, its derivative is the y value of little f. So its derivative at c is the y value of little f. And so somehow what this is saying is that the integral and the derivative are sort of opposites of each other, right? So if I take the function, it's the integral of little f. If I take the derivative, it's the y value of little f. We'll explore this more. This is called, this is part of the fundamental theorem of calculus. So this is like the most important theorem in calculus.